Dear viewers, welcome to the session. We'll continue with the module 2, wherein we have already gone through the previous sessions pertaining to the mathematical modeling of various mechanical systems. In mechanical systems, we have learned how to mathematically model or evolve a mathematical equation for linear mechanical systems as well as rotary mechanical systems. Thereafter, we have gone on to learn about the mathematical modeling of electrical systems. Then we have also learned the analogous systems from mechanical to electrical and electrical to mechanical. Now, I am going to introduce a very interesting topic to you in module 2. It is definitely pertaining to the mathematical modeling only, but still this is a very interesting issue that in order to evolve a mathematical model or mathematical equation for mechanical systems, we have seen that if the systems are simple, it is rather easy by applying the Newton's second law and evolve a mathematical model. But as the system starts getting complicated, be it a mechanical system, as the system starts getting complicated, as more number of elements get involved there, as the order of the equation starts going up, there where the derivation of mathematical modeling becomes very lengthy. We will have to handle a number of terms, as well the simplification process becomes very complex as and when the system become complex, and the system will have the mathematical equations will start getting bigger and bigger in their order. For that, we have also observed that the mathematical modeling to evolve a mathematical equation for an electrical system, no matter however simple or complex might be the electrical network, but still the process of evolving the mathematical model, whether it is a simple system or a complex electrical system, it was rather easy. Considering that, the people have come, the experts have come out with one approach that is called network approach. What we have written here is the network approach. Now, I want to highlight on one very important issue here. See, resistance, very commonly we associate the term resistance, capacitance and inductance only to the electrical system. But as we all know that those are very normal and very common terminologies, they are very common, just general English words. Right. So, resistance could be applied to mechanical engineering, resistance could be applied to electrical engineering, resistance could be applied to hydraulic, pneumatic, electrical system, thermal systems, hydraulic systems. You can apply, because resistance, the meaning or the application of the word resistance is not limited to just electrical systems, but it is also a very general word. It could be applied anywhere. Resistance, capacitance as well as inductance, those are such terminologies which are not restricted to only electrical system for their application. They are very general terminologies which could be applicable to mechanical systems, electrical systems or any other systems. Considering that, and also by the virtue of it being easy to analyze and evolve a mathematical model for an electrical network, what we tend to do is, we will consider the terminologies that are used in electrical systems such as resistance, capacitance and inductance to for the systems such as hydraulic systems, pneumatic systems, thermal systems as well as the liquid level systems to evolve the mathematical model. So, we will consider these terminologies, the resistance, capacitance as well as inductance, as applied to the liquid level systems, hydraulic systems, pneumatic systems as well as thermal systems, so that we could evolve a mathematical model, more precisely speaking, so that we could evolve a transfer function for such systems. So, hereafter all those systems, liquid level systems, hydraulic systems, pneumatic systems as well as thermal systems, where we will be carrying out the process of mathematical modeling to get the transfer function, there we will be applying the network approach, so that the analysis becomes easy, the mathematical modeling process becomes easy, and we get with very simplest process we will be able to get the mathematical model, that is the transfer function. So, for that the foundations are very important. What are the foundations? If resistance is considered in electrical network, what will be the relationship that we'll be using. If resistance is applied to hydraulic system, what will be the relationship we'll be using? If resistance is applied to a thermal system, what will be the definition and what will be the relationship we are using? Similarly, if the capacitance is applied to electrical system, what is the capacitance when we consider the electrical system? What is the capacitance when we consider the hydraulic system? What is the capacitance when we apply the same terminology to a thermal system? What definition do they give and what is the relationship they will be giving, so that we could use those definitions, we could use those relationships, so that the process of mathematically modeling such a system could be taken up and we could arrive at the transfer function that we are aiming at. Now, consider this equation itself. If you can just see over here, resistance, when the resistance is studied as applicable to the electrical system, what will be the relationship? Resistance means it is the resistance offered to the flow of charges, and the equation given is change of voltage, change in voltage to the change in current. And what is according to the Kirchhoff's law? According to the Kirchhoff's law, what does it give? According to the Ohm's law, what does it give? V is equal to IR is the relationship, where R is the resistance, I is the current and V is the voltage. Now, if we just cross multiply that, then electrical resistance can be defined as you can see over here, if the relationship between voltage and the current, if they are linear, then it will be V by I. Then if we apply the same resistance to the thermal system, then what do you mean by thermal resistance? Then obviously it is the resistance offered by the system to the flow of heat, obviously. Then if we just try to study what is the thermal resistance, then as far as the relationship is concerned, then change in temperature caused due to the change in the flow of heat. So if the relationship between the temperature and the flow of heat is linear, then obviously it will be addressed as T by Q straight away. Then if we consider the resistance as applied to the hydraulic system, then what does it mean? Obviously it will be like the resistance offered to the flow of liquid. Then if we try to know what is the relationship that we have to follow when we consider the hydraulic resistance, obviously it will be the change in the head to the change in the flow of liquid. Then if the relationship between the change in the head and change in the liquid, flow of liquid is linear, then obviously it will be H by Q, right? Then similarly, this is about the resistance as applied to electrical system, as applied to hydraulic system, as applied to thermal system. Now, if we consider the capacitance, then when we consider the capacitance pertaining to the electrical system, what is the relationship we are going to use? It is Q by V. Electrical capacitance is given by Q by E. This is derived from the basic equation. See, voltage across a capacitor. What is the voltage across the capacitor? If you recall the previous sessions wherein the electrical systems were analyzed, then you would come to know that the voltage across the capacitor, considering the Kirchhoff's law, then it is 1 by C integral of I dt. Then I is what? It is the rate of change of charges, flow of charges. Then obviously I can be replaced by dq by dt. So if you just simplify that, if you derive that, then you will arrive at the electrical capacitance will be given by the Q by V, that is so many coulombs per single voltage. Then if we consider the capacitance as applied to the thermal system, what it means by thermal capacitance, then see, thermal is what is denoting thermal capacitance. It is given by the ratio of the quantity stored to the temperature got changed. So the ratio is Q by T, watts per degree centigrades. Then if we consider the hydraulic capacitance, then obviously it is given by change in the rate of flow divided by change in the head. Now change in the rate of flow is, as we have known from the concepts of fluid mechanics or fluid machinery, then we will be knowing that the change in the flow is given by the area of the tank, area of the container into the change in the head, and dH is again change in the head. This and this goes, and the hydraulic capacitance for a hydraulic system, or the liquid level system remains to be the area, the surface area of the container which is going to store the fluid or the liquid. These are the foundations to apply the network approach to the systems such as hydraulic systems, thermal systems, and even foregoing the pneumatic systems also. That is where we are going to apply these terminologies, and so that the evolution of the mathematical model, that is the transfer function, the process of evolving a transfer function, that becomes easier. Why? Because it is by the virtue of an electrical network being easier to analyze and evolve a mathematical model or the transfer function. We are using the terminologies used in electrical network such as resistance, capacitance and inductance as applied to other types of systems such as thermal system, pneumatic system, hydraulic system, as well as the liquid level system. With this, let us start applying what we have just learned, the network approach, to the liquid level system first. Thereafter, we will proceed to apply the network approach to thermal systems, pneumatic systems, as well as hydraulic systems. First, let me take up the liquid level system examples. Liquid level systems. Liquid level systems, they are also called hydraulic systems. Now, let me consider the problem number 1, the simplest problem. What it means to say, there is a tank. There is a tank. To this tank, the liquid is flowing at a rate of Qi. So, the tank is getting filled. The tank is having the surface area A. Then, is it just filling? No. The tank has the outlet over here. The tank has the outlet. So, this is with a head of H. The tank is getting filled and the level of water filled in the tank can be considered as the head. Now, this is where the liquid is going out, and to control the flow of liquid, there is a control valve. What does it offer? What do you mean by control valve? Control valve means to say it is present to offer a resistance to the flow of liquid from the tank. So, what is it offering? Technically speaking, it is offering the resistance. Resistance. What is that resistance? It is hydraulic resistance. Why? Because this resistance is to oppose the flow of liquid from the tank. Why? Because Qi, at this rate, Qi is the rate at which the liquid is getting filled in the tank, which is having the surface area A, which is having the head H. From this tank, we are releasing water, we are releasing the liquid, and we are not simply releasing the liquid, we are controlling the flow out, the outflow of the liquid from the tank, we are controlling it. How? We have incorporated a valve. What is valve doing? It is trying to offer resistance to the flow of liquid outside the tank. So, the valve partially opened, or whatever is the opening of the valve, it is letting the liquid to go out. At what rate? It is going out at the rate Q0. This is the problem. Now, what is asked here? Obtain the, it can even be governing differential equation and the transfer function. TF is the acronym for transfer function, GDE is the acronym for governing differential equation. So, this is the question asked. What is the question asked? Obtain the governing differential equation and the transfer function for the liquid level system shown. Now, as I had mentioned during the previous sessions also, before we straight away jump into the solution, first we have to analyze, we have to plan the solution, we have to analyze the given problem. See, this is the given problem. What could be the transfer function? What is a transfer function? The definition should be recalled here. What is the transfer function? It is nothing but a mathematical equation. It is a mathematical model which represents what happens between the transformation of input to the output. So, what it means to say, the ratio of output to the input on the left hand side, then what will be remaining on the right hand side, that is what is going to be the mathematical model, or that is what is going to be called as transfer function. So therefore, what is it that you are supposed to find over here? Ultimately transfer function. What is the transfer function? What is the output from the system? Q naught. What is the input to the system? Qi. So obviously the transfer function that you are supposed to find out is Q naught by Qi. Okay. Now here, to solve this problem, to arrive at the transfer function, the governing law, just like for mechanical system, we followed the Newton's second law. We applied Newton's second law. Then for electrical systems, we applied Ohm's law and Kirchhoff's law. Whereas for a liquid level system, the governing law is apply the law of conservation of energy. That is what we acronym as LCE. Okay. Now the solution starts here, right? The solution starts here. So what are we doing? We are applying the law of conservation of energy. What does it say? Qi minus Q naught, the rate of inflow minus the rate of outflow, will be equal to the quantity of liquid that is getting stored inside the tank. Okay. Now we also know that quantity stored in the tank will be equal to, quantity stored in the tank will be equal to A into rate at which the head is going to change with respect to time. So A into dH by dt. A into dH by dt. Now if you just equate these two, what do we get here? Qi minus Q naught is equal to A into dH by dt. Now when we know that Qi minus Q naught is equal to A into dH by dt, what is the, we know now the network approach terminologies come into application. What? A is what? Surface area of the tank. According to the network approach, if you just see here, A is what? It is nothing but the hydraulic capacitance C. So I'll write it as C hydraulic. Since it is the first problem, I'll write the subscript as hydraulic so that it becomes easier to understand. Okay. Then we also know that what is the resistance offered over here? It is hydraulic resistance. Okay. Resistance hydraulic. According to the network approach, when we apply resistance to the hydraulic system, when we consider resistance in the hydraulic system, what does it give us? R hydraulic is equal to dH by dQ. We don't know whether the system is linear or not. That is why we will apply dH by dQ straight away. So R hydraulic is equal to dH, and what is this dQ? It is the outflow. dQ is nothing but the outflow, right? So that is why we consider it as dQ naught, right? Then if we just cross multiply this, R hydraulic into dQ naught is equal to dH. This is what we are left with, and if we divide on both the sides by dt, R hydraulic and dQ naught by dt is equal to, what we are left on the right hand side is dH by dt. Why we have done all this circus is so that A could be replaced by C hydraulic, hydraulic capacitance. A is nothing but hydraulic capacitance, and dH by dt could be replaced with something which is relevant. Why we are worried about substituting or replacing dH by dt by this term is because, see, if we want to arrive at the transfer function what is wanted by us is in terms of Q naught by Qi is equal to some mathematical equation. If we are to derive this equation to the verge of just Q naught by Qi, then all the terms in the equation must be either in Qi or Q naught. Now, with having A into dH by dt, we don't have any term here which is Qi or Q naught. So, related, we are just using the network approach relationship as applied to the hydraulic systems, and thereafter what we have got is dH by dt could be replaced by R hydraulic into dQ naught by dt. If we write it here, then A is nothing but C hydraulic is C, then dH by dt is nothing but R. I am just not writing hydraulic over here because this was for understanding, R into dQ naught by dt. Now, once we have written this, see all the terms are either in Qi or Q naught. So, because of which what we can write over here is Qi is equal to Q naught plus, I will rewrite it as RC dQ naught by dt. Now, this is nothing but the governing differential equation. Now, this is the governing differential equation. We have to arrive at the transfer function. That is why what we will do here, the old procedure what we used to do, apply Laplace transformation to the governing differential equation. Therefore, what will happen is Qi will become Qi of S, then Q naught will become Q naught of S, as well dQ naught by dt will become S Q naught of S. Now, if we apply this, then what we get here is Qi of S is equal to Q naught of S plus RC S into Q naught of S. If we just take out Q naught common on right hand side, we will get 1 plus RCS inside the bracket and here as Qi of S. Now, if you just cross multiply, then what you get over here is 1 by 1 plus RCS. This is what is the transfer function. This is what the simplest way in which we can arrive at the transfer function for such a problem given. Now, let me take up, just like in mechanical system, we started with the simplest single mass spring damper system. Even in liquid level system, we can have more than one tank here. Just like we had more than one mass, we can have more than one tank. We can have two tanks, we can have even more than that. So, let us switch over to the problem number 2. Again here, you need to find out the transfer function ultimately. The problem given to us will be a tank is there which is getting filled with liquid with the rate of flow as Qi. Then it is maintaining a head of H1. Then the area, surface area of the tank is A1. Then the tank is discharging the liquid. The tank is discharging the liquid and in a controlled fashion. Just like here also it will be released. The liquid is released from the tank in a controlled fashion with the presence of control valve, which is offering a resistance R1, hydraulic resistance R1. Then what is coming out from here is Q1. It is not Q naught. Why? Because we are considering a problem which is having two tanks. Now, this Q1 becomes the input to another tank this Q1 has become the inflow, the rate of flow, inflow to the tank 2 with an area A2 with a head, maintaining the head H2, and this tank in turn is releasing the liquid outside again in a controlled fashion because of the presence of control valve, which is offering the hydraulic resistance R2, because of which the liquid flowing out is at the rate of Q0. This is the problem given. What is supposed to be found out over here? We can simply say find the transfer function. Find the transfer function. It can be asked to find out Q0 by Qi. It can be asked to find out the transfer function Q0 by Qi, or even if it is not asked, we can still understand that in this particular given problem, the transfer function to be found out is Q0 by Qi. To this particular problem, just like in mechanical systems, we considered one mass at a time. Then we applied the Newton's second law to one mass at a time, and then we came out to the governing differential equation. Then we applied Newton's second law, we wrote the functional block diagram, we applied Newton's second law, and we came up to the governing differential equation for another mass also. Then what we did was, whatever transfer function we wanted, accordingly we made the substitutions for the governing differential equation of mass 1 from mass 2 or mass 2 from mass 1. Thereafter, we just iterated till we got the required transfer function in our problem. Same thing here also is applicable. You can consider tank 1 in place of mass 1. So, with that in mind, we will apply the law of conservation of energy that has been acronymed as LCE. Apply the law of conservation of energy for tank 1. Then when we did that, then Qi will consider this tank first up to this, the system up to this from the problem. So, Qi minus Q1 is equal to the quantity of fluid stored, as we are all aware. Now, we also know that QS1 is nothing but A into dH by dt. We are also aware that QS1, quantity of fluid stored in the tank 1, will be equal to area, surface area of the tank A1, as has been given in the problem. Then dH1, change in the head dH1 of the tank 1, change in the head of the tank 1 dH1 with respect to time. So, QS1 can be written as A1 into dH1 by dt. That when we substitute in this equation, then when we get Qi minus Q1 is equal to A1 into dH1 by dt. Now, again use all the network approach terminologies. So, there what will happen is A1 is nothing but, I will just make some substitution over here. Yes, see, hydraulic is nothing but, as per the derivation over here, dq by dh. So, A1, since we are considering it for tank 1, C1, and tank 1 is having the area, dq is nothing but area into the change of head. So, A1 is the surface area of the tank, dH1 is the change in head. So, in the denominator also it will be dH1. So, dH1 goes, we are left with hydraulic capacitance of tank 1 will be equal to the surface area of the tank 1. So, this is what we can substitute for A1. Then, we also know that the hydraulic resistance for the tank 1 will be given by hydraulic resistance R hydraulic or R1 is given by dH by dQ. the hydraulic resistance is given by dH by dQ. We will just rewrite dH by R1 is equal to dH1 by dQ1. dH1 by dQ1. Now, if we just try to cross multiply this, what we can say is R1 dQ1 is equal to dH1, and further what we can write is R1 dQ1 by dt is equal to dH1 by dt. Why we have derived dH1 by dt in terms of R1 into dQ1 by dt is because, see, the transfer function is to be attained in terms of Q0 by Qi. So, for that we do not want any dH terms to be present in the equation. So, either we want for tank 1, we want all the terms either in terms of Qi or Q1. So, with this network approach utilization, what we have been able to do is, we have been able to find equivalent terminology, equivalent relationship for dH1 by dt in terms of Q1. So, this is what we have substituted over here. Then what we get, Qi minus Q1 is equal to A1 has been replaced by C1, then dH1 by dt has been replaced by R1 dQ1 by dt. Now, just rewriting it, Qi minus Q1 is equal to C1 R1 into dQ1 by dt. Apply Laplace transformation for that. Then Qi becomes Qi of S, Q1 becomes Q1 of S, then dQ1 by dt becomes S, d by dt is replaced by S, S into Q1 of S. That is what we have done over here. Then we will arrive at, just by taking all Qi terms on one side and Q1 terms on the other side, we will arrive at this equation. This is what is the governing differential equation for tank 1. Same thing we will be doing it over here. For tank 2, if you consider, this is tank 2, if you consider Q1, the output from the tank 1 is Q1. This becomes the input to the tank 2. This becomes the input to the tank 2. So, Q1 is the input to the tank 2. Q0 is the output from the tank 2. The procedure 100% remains the same what we have done it for tank 1. So, Q1, according to the law of conservation of energy for tank 2, Q1 is Q1 minus Q0 is equal to Qs2. We also know that Qs2 is nothing but for tank 2 A2 into dH2 by dt. That is what we have written over here. That is why it becomes Qi, Q1 minus Q0 is equal to A2 into dH2 by dt. I think this is not properly written. A2 into dH2 by dt. Now, thereafter, as we have done it over here, A2 is nothing but, as per the network approach, A2 is nothing but hydraulic capacitance of tank 2. So, that is one. Then, this is what has been derived over here. Then, dH2 by dt, R2 hydraulic resistance for tank 2 is nothing but dH2 by dQ0. dH2 by dQ0. Again, if we cross multiply and divide it by dt, then what we get over here is dH2 by dt is equal to R2 by R2 into dQ0 by dt. That is what we have replaced over here. So, in place of A2, we have written hydraulic capacitance C2. In place of dH2 by dt, again we wanted in terms of Qi or Q0, Qi, Q1 or Q0. We did not want any of the terms of the equation to be in terms of H or dH1 or dH2. That is why, using the hydraulic resistance terminology or relationship from network approach, what we have done over here is we have found the replacing term for dH2 by dt in terms of Q0 over here as applied to tank 2. So, that is what we have replaced over here. So, then if we just rewrite it, Q1 minus Q0 is equal to R2 C2 into dq naught by dt, that is what we get. Apply Laplace transformation, then q1 becomes q1 of s, q naught becomes q naught of s, and d by dt is to be replaced by Laplace transformation s. So this becomes s into q naught of s. That is what we have written over here, and when we bring all q1 terms on one side and take q naught terms on the other side, this is what is going to be the equation. This is named as equation 2, and this is nothing but the governing differential equation for tank 2. Now, what do we want? We have got two governing differential equations, and now what is our next objective is we have to arrive at the transfer function in terms of q naught of s by qi of s, as has been asked in the question, or even if it is not asked in the question, we have to arrive finally at q naught of s by qi of s. How do we do this? See, equation 1 is in terms of qi and q1. Equation 2 for tank 2 is in terms of q1 and q naught. What is common between them? q1 is common between them. So what we can do over here is, from the equation 2, the replacing term for q1 is present on the right hand side, which is in terms of q naught. So if we substitute for q1 from equation 2, if we substitute the value of q1 from equation 2 into equation 1, then what will happen? In place of q1, I will be writing the right hand side of equation 2. This is what we have done over here. Substitute equation 2 in equation 1. Then what did we get? qi remains qi on one left hand side. Then 1 plus c1 r1 s remains the same on the right hand side. And in place of q1, what I have to write? 1 plus c2 r2 s into q naught of s. This is what has been written over here. Once we write this, what is left over here? See, the complete equation is in terms of qi and q naught. So that is what we wanted. All this circus has been carried out only to arrive at such an equation. Then what we can do? We can just cross multiply. We can retain q naught on one side, cross multiply this, qi goes to the denominator, and then what will be left with us is on the other side, it will be 1 divided by 1 plus r1 c1 s into 1 plus c2 r2 s. This is what we have got. This is what is the transfer function which has been asked to be driven over here. Now let us get into one more problem. The previous problem what we have solved, that is problem number 2, there one tank was above and another tank was below, because of which we could have considered one tank at a time, and we could have gone on to find the transfer function in terms of q naught by qi. Whereas here, if you look at, this is again a problem of liquid level systems wherein there are two tanks. This problem is also having two tanks, but the thing is, as you can see, the tank 1 as well as tank 2, they are more or less on the same surface. The tank 2 is not below tank 1, just like in the case of problem number 2. Then there rises a problem, right? So given two tanks are there, tank number 1, this you can find it even in the rooftops of many of the houses where there are more than 2 overhead tanks at your houses, right? There, do you keep the tanks one below the other? You don't do it. You normally keep both the tanks in line with one another, and you will be giving inflow to one of the tanks, and once that tank gets filled, the water starts moving to the another tank, and the parallel filling of the tanks, even if there are 2 tanks or 3 tanks, if they are all placed at the same level, obviously the parallel filling of the tanks will take place. You can consider that, you can keep that in mind, and you can just see what will be the transfer function of such a liquid level system wherein 2 tanks are placed in line with one another, and the inflow to the tank 1 is qi. Tank 1 is having the surface area A1 and the head is H1, and the liquid is discharged through this tank 1 through the control valve, which is showing the resistance. The control means what? Control is nothing but resisting the flow. So the control valve is offering a resistance of R1, because of which the liquid that is flowing out of the tank 1 becomes Q1. So, Qi is the input, inflow, then Q1 is the outflow or output from the tank 1. Then Q1 becomes the input to tank 2, which is having the surface area A2. Tank 2 is having the surface area A2, and the head for the tank 2 is H2, and again from the tank 2 also the liquid is released, and not just released at a controlled rate. So, because we are incorporating a control valve, it offers a resistance R2 to the flow of liquid. So, that is why hydraulic resistance for the tank 2 is going to be R2. Then the liquid that comes out of the control valve of the tank 2 after being resisted with the hydraulic resistance R2, the flow rate from the tank 2, the outflow will be equal to Q0. So, ultimately 2 tanks, if we consider 1 tank at a time, which is actually the procedure to follow, then Qi is the input to the tank 1, Q1 is the output from the tank 1, Q1 becomes the input to the tank 2, and Q0 becomes the output from the tank 2. Now, what has been asked to find? What is it that we are supposed to do? The question is written over here. Given this system, we are supposed to obtain the governing differential equation for these cases relating Qi and H2. This is something new, because previous problem we did not have such a limitation. We have to find the governing differential equation for this given system relating Qi and H2, relating Qi and H2. Then again we have to find the governing differential equation relating Qi and Q0. Then we are also supposed to find the overall transfer function for the given system. Now, let us take the case 1 first. We will try to find the governing differential equation relating Qi and H2. Now, we will consider the procedure remains the same. We will consider 1 tank at a time, then we will apply the law of conservation of energy, then we will arrive at the governing differential equation. And in between, we will be using the network approach terminologies such as hydraulic resistance, then hydraulic capacitance. As such, the relationship that we have known now in the network approach introduction, those terminologies or those relationships we will be making use of to find the governing differential equation and relating Qi and H2 as well as Qi and Q0. But the basic governing law for the hydraulic system is the law of conservation of energy. Now, let us consider the case 1. In case 1, let us consider the tank 1. Tank 1. To this tank, apply the law of conservation of energy, which says Qi minus Q1 is equal to quantity of liquid stored in tank 1. Then we also know that the quantity of liquid stored in this tank 1 is also equal to the surface area of the tank into rate of change of head dH1. So, that is what is A1 into dH1 by dt. So, what it means to say, then we will replace Qs1 by A1 into dH1 by dt. Now, we also know that from the network approach, the hydraulic resistance for tank 1, that is nothing but C1, it is nothing but the surface area of the tank, that is what has been written over here. Then we also know that since the 2 tanks are on the same level, not one below the other, because of which the hydraulic resistance for the tank 1, for the flow of liquid from tank 1 will be equal to hydraulic resistance for the tank 1, R1 will be equal to H1 head in the tank 1 minus head in the tank 2 divided by Q1. Now, to make it understand easily, what example I can quote is, we have come across the mechanical systems wherein spring mass damper systems were considered. If there are 2 masses and one of the spring or one of the damper is connected to both mass 1 as well as mass 2, what did we used to do? The resisting force offered by the spring will be nothing but the stiffness of the spring into the displacement of mass 1. If we are considering mass 1, then the displacement of mass 1 minus the displacement of mass 2. Why? Because if K1 is the spring force, spring stiffness, and M1 is the mass, X1 is the displacement of mass 1 and X2 is the displacement of mass 2. And if the spring is connected to both mass M2 as well as M1 over here, then the moment the mass tends to get displaced, the spring will try to pull the mass 1 back. Then by what force? K1 into X1. When it tries to pull back the mass M1, since the spring is connected to mass M2 also, it will try to push back the spring by the force K2 into X2. Therefore, the effective resisting force offered by the spring will be equal to K1 into X1 minus X2. The same thing is applicable over here. The moment the resistance is considered for the flow of liquid from the tank 1 towards tank 2, since both the tanks are at the same level, what happens is, the moment it tries to offer resistance, then that resistance is opposed by the presence of tank 1. By what? By the presence of head H2. Therefore, the effective resistance offered by the control valve with hydraulic resistance 1 for the tank 1 will be equal to H1 minus H2 divided by the flow of liquid from tank 1, that is Q1. So, this is what is the major understanding or major change compared to the previous problem. Now, R1 is equal to H1 minus H2 by Q1. We just cross multiply this. R1 into Q1 is equal to H1 minus H2. Then we will just try to take H1 on one side and R1 on the other side. Why? Because we should never forget that, as I have told you, we should always plan the solution. What is it that we are trying to find? We want the relationship governing differential equation, total governing differential equation in terms of Qi and H2. So, wherever possible, we have to keep on finding opportunity to find the relationship in terms of H2 and Qi. So, here in this term, we can find in place of H1, we can write R1 into Q1 plus H2. How did we get with this? Now, if you R1, H1 is equal to R1 Q1 plus H2, I cannot directly put it over here. Why? Because here, as you can see, I want dH1 by dt, I don't have just H1, because of which I will differentiate this equation, then dH1 by dt is equal to R1 dQ1 by dt plus dH2 by dt, that is what I get here. So, thereby, since dH1 by dt is there, I can replace dH1 by dt by this particular term, R1 dQ1 by dt plus dH2 by dt. That is what I have written over here. In place of A1, I have written C1. In place of dH1 by dt, I have written this terminology. It is just rewritten over here. To this equation, I will apply Laplace transformation. What does Laplace transformation say? Qi becomes Qi of S, Q1 becomes Q1 of S, and dQ1 by dt becomes S into Q1 of S. That is what it becomes. So, this is what I have written over here. Then, now let us come to tank 2. Then tank 2, it is just like any simple tank. Here this problem does not come into picture. Resistance will be equal to H1 minus H2 by Q1 for tank 1. That problem does not come into picture. Therefore, for tank 2, if you apply law of conservation of energy over here, apply law of conservation of energy over here, then Qi becomes the input to the tank, Q0 is the output from the tank. Therefore, Q1 minus Q0. Q1 is the input to the tank 2. Q0 is the output from the tank 2. Therefore, Q1 minus Q0 is equal to Qs2 actually. Qs2, then we know that Qs2 is equal to A2 into dH2 by dt. Therefore, Q1 minus Q0 is equal to A2 into dH2 by dt. Then Q0, as you can see over here, Q1 we will retain as it is. A2 we know that it is C2. Hydraulic capacitance of tank 2 is nothing but the surface area of tank 2. Then dH2 by dt in the all previous occasions, we have tried to replace dH2 by dt in terms of either Q0 or Q1 or so. Whereas here, considering the question in terms of Qi and H2, we need to find the governing differential equation in terms of Qi and H2, because of which we will not replace for this dH2. Instead, for this Q0, we will try to find something in terms of H2. That is what has been written here. Hydraulic resistance for the tank 2 R2 is equal to dH2 by dQ0 is the relationship. Therefore, since the situation here is linear, so what we will do is dH2 by dQ0 can be rewritten as H2 by Q0, and then if we just cross multiply this on the other side, then we will get Q0 will be equal to H2 by R2. That is what has been written here. Now if you can just see Q1, this equation becomes in terms of Q1 H2 as well as Q1 and H2 only. Then we will name this, we will just rewrite this equation, we will get Q1 is equal to C2S into H2 plus H2 by R2. Now, if you compare this equation and this equation, what can you assess? See, this equation is in terms of Qi, Q1 and H2. And here this equation is Q1 and H2. So, what it means to say is, you have found out the replacement for Q1. The right hand side of this equation is nothing but the replacing term for Q1 in this particular equation. So, if you just see, if you substitute the value for Q1 from this equation into this equation, right, see here, if you just denote this into this as equation 1 and this as equation 2, then if you substitute equation 2 in equation 1, then in place of Q1, see here there is Q1, here there is Q1, then in place of Q1 you can write all these terminologies. That is what has been written over here. Then you would come to know that you will find everything in terms of Qi and H2. If you just rewrite this, then you will be left with R2 Qi on one side and rest everything in terms of H2. That is what is asked over here. The governing differential equation you have found out for this system in terms of only Qi and H2. Now, if we look at the second sub question, we need to find governing differential equation in terms of Qi and Q0. See, this is the solution, case 2 and 3, case 2 and 3. For the tank 1, if it's just see from the law of conservation of energy, Qi minus Q1 is equal to Qs1, as you have known. Qs1 is already known to us, that is, it is A1 into dH1 by dt. Then it can be rewritten as, and A1 is nothing but the hydraulic capacitance C1. Then resistance R1 is H1 minus H2 by Q1, and here R1 Q1 is equal to H1 minus H2. H1 you have found out in terms of Q1 and H2. Okay. Now, this you can, if you differentiate just like what we have done over here, we will get dH1 by dt is equal to R1 dQ by plus dH2 by dt. This is dQ1. Okay. Then R1 dQ1 by dt you have got, then dH2 by dt is there. dH2 by dt is nothing but, dH2 by dt is nothing but, if you just see, if you consider the hydraulic resistance for tank 2, then hydraulic resistance for tank 2 is given by dH2 by dQ0, dH2 by dQ0. Now, if you just cross multiply, you will get R2 dQ0. If you just cross multiply, you will get R2 dQ0 is equal to dH2 divided by dt. You will get R2 dQ0 by dt as the replacement for dH2 by dt. And you know that the surface area of tank 2 is nothing but the hydraulic capacitance of tank 2. If you try to replace all these terms in this particular equation, then Qi minus Q1 remains the same, then is equal to C1 is equal to then C1 into this equation R1 dQ1 by dt plus dH2 by dt. Now you can find the replacement for dH2 by dt also. dH2 by dt is equal to R2 dQ0 by dt. That is what has been written over here. R1 C1 dQ1 by dt plus in place of C dH2 by dt, C, this is C2, sorry, in place of C1 dH2 by dt, C1 remains the same, whereas dH2 by dt, as you have found out over here, it is nothing but R2 into dQ naught by dt. That is what you have written over here. Now, once you have written that, apply Laplace transformation, then Qi becomes Qi of s, Q1 becomes Q1 of s, and d by dt goes as the Laplace transformation. Yes, therefore, Qi minus Q naught will be equal to R1 C1 into d by dt becomes yes, Q into Q1 plus R2 C1 d by dt becomes yes, so into Q naught. So, if you just rewrite it, keeping Qi on one side, you will get R1 C1 yes into Q1 yes plus R2 C1 yes into Q naught of s plus Q1 of s. Name this as equation 1. Now, consider tank 2. If you apply law of conservation of energy, to tank 2, then you will get Q1 minus Q naught is equal to QS2. That is what has been written over here. We know that QS2 is equal to A2 dH2 by dt. So, when we know this, we will replace QS2 by A2 into dH2 by dt. Then Q1 minus Q naught will retain. A2 is nothing but hydraulic capacitance of tank 2, that is C2. R2 is equal to dH2 by dQ naught, we know that. Then you just cross multiply R2 into dQ naught is equal to dH2, you will get, divided by dt, you will get R2 dQ naught by dt is equal to dH2 by dt. That is what you will be replacing in place of dH2 by dt. Why all this we are replacing H2 everywhere is because H2 by either Q naught or Q1 is because the question asked is you need to find the governing differential equation in terms of only Qi and Q naught. That is why you are trying to find the replacement for dH2 everywhere. That is why all the network approach terminologies have been used over here. Now, once you get the replacement for dH2 by dt as R2 dQ naught by dt, you are putting it in this equation. Therefore, Q1 minus Q naught is equal to C2 R2 into dQ naught by dt. Now, you just, the entire equation is in two terms. One, either it is Q1 or it is Q naught. If you can see here also Q naught, here also Q naught. You will retain Q1 on one side, bring all Q naughts on other side, you will get this equation. Apply Laplace transformation to this equation, you will get Q1 of s is equal to Q naught of s plus C2 R2 s into Q naught of s. Now, what it means to say is you have found out the value of Q1 in terms of Q naught. You know equation 1 wherein Qi of s has been found in terms of Q1 of s. So, since Q1 of s has been found over here in terms of Q naught, you substitute equation 2 in this equation 1, then what happens? All Q1s in equation 1 will be replaced by the right hand side of equation 2. That is what has been written over here. Then once you substitute Q1 values in terms of in the equation 1, where you are arriving at an equation which will be in terms of only Qi and Q naught. That is what is the question asked, sub question 2. What it means to say governing differential equation in terms of only Qi and Q naught. If you can just observe this equation, it is only Qi or and just Q naughts. This is the answer for sub question 2. Then what is the final ask? We need to find the transfer function. What is the transfer function? We need to find Q naught of s by Qi of s, because for this system input is Qi, output is Q naught. So, we need to find the transfer function. Once we have found it, we are just 1 or 2 steps away from the final transfer function. What is that? You just take out Q naught as common everywhere, you will be left with this equation inside the bracket into Q naught. Once you find that, you just cross multiply, bring Q naught on the numerator, then cross multiply, Qi goes to the denominator. What you will be left over here is 1 divided by R1 R2 C1 C2 s square plus in brackets R1 C1 plus R2 C2 plus R2 C1 in close the bracket s plus 1. This will be the final transfer function that will be arriving. So, with these problems, what it means to say is no matter the systems that we have taken up for problem solving, although it is mechanical, although it is hydraulic systems, the basic fundamental remains the same. If there are two masses, then take one mass at a time and then the next mass. Like that, even if it is a liquid level system, consider one tank at a time and then get going with it. And one more time, network approach is a wonderful improvisation in the process of problem solving, because it is by the virtue of this approach, by the virtue of it being easy to analyze the electrical networks, the terminologies that have been used in electrical networks or electrical systems have been taken up or adopted over the here in other various systems such as hydraulic systems, liquid level systems, pneumatic systems or thermal systems. Thereby it has made it a lot easier to solve the problems and arrive at the what has been the basic requirement of this particular module, that is mathematical model, that is nothing but the transfer function. Thank you.